Okay, so you are learning Newton's first law, equilibrium, tension, normal reaction. How's it going so far? So far so good. Okay, let's see. This block is of 10 kg mass, and the question this time is how much of the force is that rope string exerting on this pulley? Pulley you must be knowing, right? Pulley is a kind of disc. It's a disc on which the rope is well seated and it can rotate around this point. And pulley you must have seen in the old kind of wells where you have an arrangement like this and the bucket goes into the well and somebody is pulling it from the other side. Pulley is very convenient because when you have a pulley like this, you can stand up straight and pull the rope horizontally. You don't have to bend over the well to bring the water outside. So your back is straight. You don't have a problem of back pain in this way. So it is advantageous. There are other advantages of this as well, which we will be talking later on. But pulley is a kind of disc on which the rope is well seated. It can rotate with the when the rope comes down, the pulley will be rotating around the center. So it's that kind of mechanical arrangement. So nevertheless, in this case, the whole system is in a static equilibrium, and you have been asked how much of force is the string exerting on the pulley. Can you find that, please? How much of force is the rope exerting on pulley? Tension finding the tension now should be pretty straightforward. The tension in this case will be 100 Newton from the equation of vertical equilibrium. This is 100 Newton. If now you have to find the force on pulley, right? So you should be trying the FBD of pulley. There's a string and this is a rod. These two are strings. The tension is 100 Newton, and we had the discussion before that tension always acts away from the body. So 100 Newton at this end of the pulley will be acting downward, and 100 Newton at this end of the pulley will be acting towards left. So this is how a string would be applying force on the pulley. And you were asked how much of the force the string applies. The string applies these two forces, so it will be a vector summation of these two forces. And you know the vector summation of two vectors equal in magnitude and perpendicular to each other, that is a root 2. So the force that the string is applying would be 100 root 2. And how does it stays at equilibrium? The net force will be 100 root 2 in this direction, and the rod will be pulling it on the other side. So 100 root 2 of force will also be applied by the rod to keep the whole pulley system in equilibrium. So nevertheless, the force which the string is applying is 100 root 2 and not 100. Vector summation. Okay? Okay. Let's suppose we have an arrangement in which this block, the weight of this is 700 Newton. Then what will be the mass? The mass would be 70 kg, isn't it? So this is given to you. This is 30 degrees, 700 Newton, and it is said that the breaking strength of the string, which is attached with this block of 700 Newton weight, this string and this string, the breaking strength is 175 Newton. So they are asking what is the maximum weight of this block, which is hung like this, that can be sustained in a static equilibrium without breaking the string. Understood? So what are you waiting for? Solve it. If we keep on increasing the tension in a string, suppose there's a string and we are stretching it from both sides, at a certain point of time the string will break. So there's a maximum tension bearing capacity of the string. There's a breaking strength if the tension exceeds that limit, then the string will break. Similarly, if the tension goes more than 175 Newton in this string, the string will break. So from the static equilibrium condition, you have to find out the maximum mass at which the tension just becomes 175 Newton. So that if you increase the mass a little bit, the tension increases a little bit, that goes above the breaking strength and it will break. So in that limiting condition, when the tension is just equal to 175 Newton, that is the maximum mass that you can hang from here. So let's start writing this equation of static equilibrium. This tension, this T, this is T, and this T will be equal to, if suppose the weight is W, then T will be equal to W from the vertical static equilibrium condition. So this is T, and let's see, this, let's call it as T1, and this, let's call it as T2. Okay, now at this point, in this point mass, let's draw the FBD of this point mass. The FBD is something like this, T2, 30 degree. This T1, T is pulling, tension is always away from the block, so it will be acting downward. The T for this will be acting downward. For T at this end will be acting upward, away from the body, all away from the body, T1. Now T2 cos 30 degree, the horizontal equation of equilibrium will be equal to T1, and T2 sine 30 degree will be equal to T. Now the breaking strength is 175, so T1 should not exceed 175. So this means that T2 cos 30 degree should be less than or equal to 175. So this means that this is T2. T2 is less than equal to 350 by root 3. Okay, so T must also be less than equal to 350 by root 3 into sine 30 degree, which is equal to half. So T must be equal, less than equal to 175 by root 3. This is your answer. Okay, easy.